Okay, next. Let me do a little bit of an overview. There was this, depending on how your instructor did it, in the solubility chapter, there was really, I would say, 5 sections. So, not 5 sections, 5 types of problems you could have seen. I want to go over those types and then I'll do a couple of them as actual examples. Okay, number 1, it could have been a KSP, a simple ice table. Okay, so for these, you want to make sure that given any compound, let's say aluminum sulfate. Let's say we had that. Not sure if it's a solid. Let's pretend it's a solid though for our sake here. Should be able to write any a KSP reaction for any compound you're given. Plus, I'll put the sulfate down here. Okay, make sure you can write that. Make sure you can write the KSP. And then make sure you can find the molar solubility. Okay, so make sure you can do that for any compound. We would usually give you the KSP. The only other way to do that is if we give you the molar solubility and we ask for the KSP. It's really the only way that one can go. Okay, second is the common ion version of the KSP problem. Okay, so let's say we have the same reaction, for example. So I'm going to just write this reaction again. Oops. Aluminum sulfate goes to 2 aluminums, aqueous, and 3 sulfates. Aqueous. Let's say we had something like that. We have an ice table going on. Let's say you wanted to find the molar solubility. You would ignore the solid. Now, typically in case 1, you would go 0 and 0 here. But let's say there was a common ion like sodium sulfate or something like that. And let's say this was 1 molar. So what does that do? That puts this 1 right there. So you get this right here, that's the common ion problem. Otherwise, you should be able to solve this, 2x plus 3x, 2x, and 1 plus 3x. Is x going to be large or small right here? Small. Typical KSP problem, x is small. Okay? All right, so that'd be a classic common ion problem. That's good. Somebody asked me about common ion. I'm going to cross that one off too. 3. Okay, there's the precipitation problems, of which there are 2 types. One type is, will it precipitate? So there's some sort of question about, does a precipitation occur? The second type is a fractional precipitation. This is if you have more than 1 ion, which one precipitates first? Okay, so they're different. A or B, which one uses Q? This uses Q, this one uses K. So make sure you get those straight, which one you're using. Which one of these could use the dilution, a dilution sort of formula? Mostly A. It could happen with B too. So just watch out that you might use this. How do you know you would use this? Again, most likely in A, for sure. Possible in B, but more likely in A. It's when you're mixing 2 things together. So if you're saying you're mixing 2 solutions together, you better be on this formula right there to find the new molarities before you start the problem. Okay. That's 3. 4. 4 is your classic KF sort of problem. The formation of a complex ion. Complex ion is something that has a transition metal in it. So let me make up one. Let's do this one. let's say I gave you this compound, and I wanted you to write the KF expression, reaction for it. You would write the ions. Usually everything's aqueous unless there's water. This one happens to have water, so the water has to be written as a liquid state. Make sure you got the states down. Then we got cobalt, that compound. So make sure you can write this explicitly, and you can write the KF expression, products over reactants. If you can write all that sort of thing down. Okay, if it's a classic one of these, then you just go straight to the ice table. We like to make these more exciting sometimes because then I don't want you to get bored. So, where should this might sound weird to those who are not in my class, but products or reactants, where should you be seeing a 0 in order to start the ice table? Right side or left side? Yeah, and the unfavored, which is the left side. So remember, KF is large. So over here somewhere, on the left-hand side, you need a 0 on that unfavored side. Okay? If you don't, you can't start the problem. So it's possible, I'll write this in different color, sometimes for fun, this could use this if there's a mixing together, occasionally. Or you might have to do stoichiometry before you go to the ice. That's if you don't have a 0 here. Okay, when you get to the point of doing the ice table, is X large or small? Small. So X is going to be small. It's going to shift back to the left-hand side. You'll have a plus X over here somewhere. Well, on both of them, you have a plus X. And that X is going to be small. So remember, you can drop out that X in this kind of problem as well. That'd be kind of your classic KF sort of problem. And then number 5, which somebody also asked me, I don't know what the other instructors call this, but I call these a mixed K sort of problem. Okay, this is where we've got one compound dissolved in another compound. Okay, this one is related to KSP, so some insoluble compound. And this one is not a common ion, something totally different than the first thing, but it helps the first thing dissolve, whatever that second compound is. I'll see if I have an example. So we've got a KSP. This will either be, this one right here, will either be a KF or something related to an acid or a base. Okay? So I say mixed K because there's more than one K involved in this reaction here, or this problem. And this will have 2 reactions that you need to add together. So you're going to add them. And after you do that, you're going to go to the ice table. Okay? This is unlikely, 2 things. Unlikely to have stoichiometry. And number 2, it's unlikely to have an X that is small. Unlikely to have stoichiometry and unlikely to have an X that is small. Okay, those are all the types. Let me take a look at what type you wanted to see. I have, probably for most people, 3, 4, and 5 are the hardest. I have one, somebody asked me about precipitation, and I have a precipitation problem I think I didn't do in class, and this one's awesome. Yeah, it's a combo problem. I don't think I did this in class. Does it look familiar to any of my students? No? Yeah, I'm pretty sure I didn't do it. I was saving it. Okay. So this is just one stop. I'll have to flip through to see if I have other example problems or not. All right, let's try this. So we got potassium chromate added to the silver nitrate. What percent of this is left unprecipitated? So really there's a couple parts here. If it was the final, we'd have to kind of be a little more explicit for grading. So really the first part is, will it precipitate? And if we wanted to be really fun, we could say there could be a part as like write the reaction for the solubility product reaction, like the KSP reaction. Write the KSP, all that sort of thing. So we could be that fine detailed sometimes. So just read the question. But the first major part is going to be this. And then the second part will be to find the concentration of the silver ion. And the third part will be the actual question. The percent of silver unprecipitated. So you really have to go through will it precipitate, find that concentration, and then do this part. So it ends up being a three-part problem of sorts. Okay, so let's do part A. Am I going to need a dilution formula here? Yeah, two things are mixed. So it's going to mess with the concentrations. I need to find those. So let me write down the dilution formula. M1V1 equals M2V2. I want to solve for the final molarity. That's what's the most interesting to me. So that's M1V1 over V2. So that's what I'm going to use. I'll do, it doesn't matter which one I start with. I'll start with the concentration of the chromate. That's going to be its before mixing concentration, which was 0.35. Times its volume, 200, divided by the total volume, which is 200 plus 200, or 400. And I got, it just went down by half, so it's 0.175 molar. And then the concentration of the silver, this is going to be 0.01. Times its a volume before mixing, and then a volume after mixing, 400. And that's just half of that, 0.005 molar. Okay, so I needed to use the dilution formula because two things are being mixed. Now I can go to Q. This is going to be for silver chromate. So make sure you can write the Q expression. CrO4, there we go. So that's our expression. You need to be able to write by the final. Let's plug in what we got. We got 0.005 squared and 0.175. So those two molarities we just found. That turns out to be 4.4 times 10 to the minus 6. And I'll write it in a different color. KSP. For the final, this would need to be given in the question. So you'd expect this in the question, because this was just for fun. I didn't write it out, but I'll tell you right now. It's 1.1 times 10 to the minus 12. Okay, first of all, does it precipitate? Yeah, Q is larger than K, so it's going to go the shift backwards, basically towards the precipitate. So yes, PPT. Okay, because it precipitates, we will continue with part B and C. If it did not precipitate, what would we do with B and C? I mean, it's kind of a lame problem. We couldn't really do it. We need a precipitate to really continue the whole problem because it's asking about the precipitate. So it would be ridiculous if it didn't precipitate. All right, so the next part, B. What's the silver concentration at equilibrium? Let me write the KSP. The reaction that goes with it. That's this. Okay. All right. Here we know both initial concentrations. This is 0.005 and 0.175. Can I start the ice table? I can't. I need a 0 on the unfavored side over here. So you're not able to start the ice table yet. You have to go through stoichiometry first. So we got to go through this mess. Okay. And I picked a fun one for you, so I hope you were hoping for a hard one. I didn't want to give a pansy lame one first. Okay, so I'm going to subtract the smaller number, and that will be, what number do I write here that I'm subtracting? Yeah, somebody in the front row knows this. Because there's a 2 there. Okay, so it's easy for somebody. I'm doubling whatever. To subtract the 0.005 to get down to 0 here, it's twice this number. And since there's no 2 here, I have to subtract 0.025, or half of the 0.005. Good. 0.173 is what I get here, and 0 there. Now, can I start the ice table if I write I there? Yeah, the ice table can now be started because I have a 0 on the unfavored side. So I'm going to add 2x here and add x here. Or 2x and 0.173 plus x. Or if I write the KSP expression, KSP, which I told you was 1.1 times 10 to the minus 12, that was the given, equals the 2x squared times the 0.173 plus x. Okay, I want to, before I continue to solve this, I want to highlight the 2. See this 2 right there? That 2, whenever it's not a 1, my class at least, well, maybe everybody knows this. How many times maximum could that appear in your calculations? 3, and that's what we saw here. Once in stoichiometry, right there. Once in stoichiometry, once in the C line of the ice table, and once as an exponent in your KSP expression. Now, sometimes there's not stoichiometry, so it'll just be 2 times. But when there is stoichiometry, you're going to have this additional 2 there. So you keep that in mind. The stoichiometry, I'm looking for that 2 somewhere. All right. Is x small here? Yeah, if you're doing a KSP problem, x is small. That could drop out. And I got x is equal to 1.3 times 10 to the minus 6 molar. Or I cared about the silver concentration at equilibrium, which is equal to 2x, or double that number. 2.6 times 10 to the minus 6 molar. So there's really part B, the silver ion concentration. This would also be called what? X. The molar solubility. That's also, if we ask for the molar solubility, it would be that number. The last part was the percent unprecipitated. See? To get the percent unprecipitated, so how much silver is left over, it's the amount of silver at equilibrium, 2x, divided by the initial amount of silver, times 100. So 2x, that was 2.6 times 10 to the minus 6 molar, divided by initial was 0.005 molar, and times 100, 0.052%. So that's the amount of silver left in solution that's unprecipitated. So not too much. Okay, let me give you a moment to think about that. See if you have any questions over all of that mess I just went over. And then I'll go to some exam 2 and 3. There was a question? Raise your hand, wave around. Yes? Oh, good. Good.
And the subtract
The question was for stoichiometry, why did I not go to moles? That's good. So sometimes you don't have to with the volume is staying constant. But you can, in my case, or in this case, we were at 400 milliliters. So if you wanted to do that, which is totally fair, I wasn't thinking about that when I did the problem. You multiply this by 400, this by 400. So this number itself would be different, but it'd still be 2 times that. So the mechanics of it would be the same, and then you divide by 400 going into the ice table. Good. Good observation. This out of the way. Okay.